In mathematics, a sheaf is a tool for systematically tracking locally defined data attached to the open sets of a topological space. The data can be restricted to smaller open sets, and the data assigned to an open set is equivalent to all collections of compatible data assigned to collections of smaller open sets covering the original one. For example, such data can consist of the rings of continuous or smooth, real-valued functions defined on each open set. Sheaves are by design quite general and abstract objects, and their correct definition is rather technical. They exist in several varieties, such as sheaves of sets or sheaves of rings, depending on the type of data assigned to open sets. There are also maps from one sheaf to another. Sheaves with their morphisms on a fixed topological space form a category. On the other hand, to each continuous map there is associated both a direct image functor, taking sheaves and the morphisms on the domain to sheaves and morphisms on the codomain, and an inverse image functor operating in the opposite direction. These functors, and certain variants of them, are essential parts of sheaf theory. Due to their general nature and versatility, sheaves have several applications in topology and especially in algebraic and differential geometry. First, geometric structures such as that of a differentiable manifold or a scheme can be expressed in terms of a sheaf of rings on the space. In such contexts, several geometric constructions such as vector bundles or divisors are naturally specified in terms of sheaves. Second, sheaves provide the framework for a very general cohomology theory, which encompasses also the usual topological cohomology theories such as singular cohomology, especially in algebraic geometry and the theory of complex manifolds. Sheaf cohomology provides a powerful link between topological and geometric properties of spaces. Sheaves also provide the basis for the theory of D-modules, which provide applications to the theory of differential equations. In addition, generalizations of sheaves to more general settings than topological spaces, such as Grothendieck topology, have provided applications to mathematical logic and number theory. Introduction. In topology, differential geometry and algebraic geometry, several structures defined on a topological space can be naturally localized or restricted to open subsets of the space. Typical examples include continuous real or complex valued functions, n times differentiable functions, bounded real valued functions, vector fields, and sections of any vector bundle on the space. Presheaves formalize the situation common to the examples above. A presheaf on a topological space is a structure that associates to each open set U of the space a set F of sections on U, and to each open set V included in U a map FF giving restrictions of sections over U to V. Each of the examples above defines a presheaf with by taking the restriction maps to be the usual restriction of functions, vector fields and sections of a vector bundle. Moreover, in each of these examples the sets of sections have additional algebraic structure. Pointwise operations make them abelian groups. And in the examples of real and complex valued functions the sets of sections even have a ring structure. In addition, in each example the restriction maps are homomorphisms of the corresponding algebraic structure. This observation leads to the natural definition of presheaves with additional algebraic structure such as presheaves of groups, of abelian groups, of rings. Sets of sections are required to have the specified algebraic structure, and the restrictions are required to be homomorphisms. Thus, for example, continuous real-valued functions on a topological space form a presheaf of rings on the space. Given a presheaf, a natural question to ask is to what extent its sections over an open set U are specified by their restrictions to smaller open sets via an open cover of U. A presheaf is separated if its sections are locally determined. Whenever two sections over U coincide when restricted to each of I, the two sections are identical. All examples of presheaves discussed above are separated, since in each case the sections are specified by their values at the points of the underlying space. Finally, a separated presheaf is a sheaf if compatible sections can be glued together, i.e., whenever there is a section of the presheaf over each of the covering sets phi, chosen so that they match on the overlaps of the covering sets. These sections correspond to a section on U, of which they are restrictions. It is easy to verify that all examples above except the presheaf of bounded functions are in fact sheaves. In all cases, the criterion of being a section of the presheaf is local in a sense that it is enough to verify it in an arbitrary neighborhood of each point. On the other hand, it is clear that a function can be bounded on each set of an open cover of a space without being bounded on all of the space. Thus, bounded functions provide an example of a presheaf that in general fails to be a sheaf. Another example of a presheaf that fails to be a sheaf is the constant presheaf that associates the same fixed set to each open set. It follows from the gluing property of sheaves that the set of sections on a disjoint union of two open sets is the Cartesian product of the sets of sections over the two open sets. The correct way to define the constant sheaf FA on a topological space is to require sections on an open set U to be continuous maps from U to A, equipped with the discrete topology. Then in particular FA equals A for connected U. Maps between sheaves or presheaves consist of maps between the sets of sections over each open set of the underlying space, compatible with restrictions of sections. If the presheaves or sheaves considered are provided with additional algebraic structure, these maps are assumed to be homomorphisms. Sheaves endowed with non-trivial endomorphisms, such as the action of an algebraic torus or a Galois group, are of particular interest. Presheaves and sheaves are typically denoted by capital letters, F being particularly common, presumably for the French word for sheaves, faisceau. Use of script letters such as is also common. Formal definitions. The first step in defining a sheaf is to define a presheaf, which captures the idea of associating data and restriction maps to the open sets of a topological space. The second step is to require the normalization and gluing axioms. A presheaf that satisfies these axioms is a sheaf. Presheaves let X be a topological space, and let C be a category. Usually C is the category of sets, the category of groups, the category of abelian groups, or the category of commutative rings. A presheaf F on X is a functor with values in C given by the following data. For each open set U of X, there corresponds an object F in C. For each inclusion of open sets VU, there corresponds a morphism RESVU, FF in the category C. The morphisms RESVU are called restriction morphisms. If SF, then its restriction RESVU is often denoted SV by analogy with restriction of functions. The restriction morphisms are required to satisfy two properties. For every open set U of X, the restriction morphism RESU, FF is the identity morphism on F. If we have three open sets WVU, then the composite RESW, VORESVU equals RESWU. Informally, the second axiom says it doesn't matter whether we restrict to W in one step or restrict first to V, then to W. There is a compact way to express the notion of a presheaf in terms of category theory. First we define the category of open sets on X to be the category O whose objects are the open sets of X and whose morphisms are inclusions. Then a C-valued presheaf on X is the same as a contravariant functor from O to C. This definition can be generalized to the case when the source category is not of the form O for any X, C presheaf. If F is a C-valued presheaf on X, and U is an open subset of X, then F is called the sections of F over U. If C is a concrete category, then each element of F is called a section. A section over X is called a global section. A common notation for the restriction RESVU of a section is SV. This terminology and notation is by analogy with sections of fiber bundles or sections of the Et or A space of a sheaf. See below. F is also often denoted gamma, especially in contexts such as sheaf cohomology where U tends to be fixed and F tends to be variable. Sheaves. For simplicity, consider first the case where the sheaf takes values in the category of sets. In fact, this definition applies more generally to the situation where the category is a concrete category whose underlying set functor is conservative, meaning that if the underlying map of sets is a bijection, then the original morphism is an isomorphism. A sheaf is a presheaf with values in the category of sets that satisfies the following two axioms. If is an open covering of an open set U, and if S/T/F is such that S/UI equals T/UI for each set UI of the covering, then S equals T, and if is an open covering of an open set U, and if for each IA section CF is given such that for each pair UI, UJ of the covering sets the restrictions of C and SJ agree on the overlaps. C UJ equals SJ UJ, then there is a section SF such that S equals C for each I. The section S whose existence is guaranteed by axiom 2 is called the gluing concatenation or collation of the sections C. By axiom 1 it is unique. Sections C satisfying the condition of axiom 2 are often called compatible, thus axioms 1 and 2 together state that compatible sections can be uniquely glued together. A separated presheaf, or monopresheaf, is a presheaf satisfying axiom 1. If C has products, the sheaf axioms are equivalent to the requirement that, for any open covering UI, the first arrow in the following diagram is an equalizer. Here the first map is the product of the restriction maps and the pair of arrows the products of the two sets of restrictions, and for a separated presheaf, the first arrow need only be injective. In general, for an open set U and open covering, construct a category J whose objects are the sets UI and the intersections UI UJ and whose morphisms or the inclusions of UI UJ and UI and UJ. The sheaf axioms for UN are that the limit of the functor F restricted to the category J must be isomorphic to F. Notice that the empty subset of a topological space is covered by the empty family of sets. The product of an empty family or the limit of an empty family is a terminal object, and consequently the value of a sheaf on the empty set must be a terminal object. If sheaf values are in the category of sets, applying the local identity axiom to the empty family shows that over the empty set, there is at most one section, and applying the gluing axiom to the empty family shows that there is at least one section. This property is called the normalization axiom. It can be shown that to specify a sheaf, it is enough to specify its restriction to the open sets of a basis for the topology of the underlying space. Moreover, it can also be shown that it is enough to verify the sheaf axioms above relative to the open sets of a covering. Thus a sheaf can often be defined by giving its values on the open sets of a basis, and verifying the sheaf axioms relative to the basis. Morphisms. Heuristically speaking, a morphism of sheaves is analogous to a function between them. However, because sheaves contain data relative to every open set of a topological space, a morphism of sheaves is defined as a collection of functions, one for each open set, that satisfy a compatibility condition. Let F and G be two sheaves on X with values in the category C. A morphism phi GF consists of a morphism phi GF for each open set U of X, subject to the condition that this morphism is compatible with restrictions. In other words, for every open subset V of an open set U, the following diagram is commutative. Recall that we could also express a sheaf as a special kind of functor. In this language, a morphism of sheaves is a natural transformation of the corresponding functors. With this notion of morphism, there is a category of C-valued sheaves on X for any C. The objects are the C-valued sheaves, and the morphisms are morphisms of sheaves. An isomorphism of sheaves is an isomorphism in this category. It can be proved that an isomorphism of sheaves is an isomorphism on each open set U. In other words, phi is an isomorphism if and only if for each U, phi is an isomorphism. The same is true of monomorphisms, but not of epimorphisms. See sheaf cohomology. Notice that we did not use the gluing axiom in defining a morphism of sheaves. Consequently, the above definition makes sense for pre-sheaves as well. The category of C-valued pre-sheaves is then a functor category, the category of contravariant functors from O to C. Examples. Because sheaves encode exactly the data needed to pass between local and global situations. There are many examples of sheaves occurring throughout mathematics. Here are some additional examples of sheaves. Any continuous map of topological spaces determines a sheaf of sets. Let f, y, x be a continuous map. We define a sheaf gamma on X by setting gamma equal to the sections u, y, that is, gamma is the set of all continuous functions S, u, y such that fs equals IDU. Restriction is given by restriction of functions. This sheaf is called the sheaf of sections of F, and it is especially important when F is the projection of a fiber bundle onto its base space. Notice that if the image of F does not contain U, then gamma is empty. For a concrete example, take x equals c, 0, y equals c, and f equals exp. Gamma is the set of branches of the logarithm on U. Fix a point x in X and an object S in a category C. The skyscraper sheaf over X with stalk S is the sheaf Sx defined as follows. If U is an open set containing X, then Sx equals S. If U does not contain X, then Sx is the terminal object of C. The restriction maps are either the identity on S, if both open sets contain X, or the unique map from S to the terminal object of C. Sheaves on manifolds. In the following examples, M is an n-dimensional CK manifold. The table lists the values of certain sheaves over open subsets U of M and their restriction maps. Pre-sheaves that are not sheaves. Here are two examples of pre-sheaves that are not sheaves. Let X be the two-point topological space, X, Y, with the discrete topology. Define a presheaf F as follows. F equals R, F equals R, F equals R times R times R. The restriction map FF is the projection of R times R onto its first coordinate. And the restriction map FF is the projection of R times R onto its second coordinate. F is a presheaf that is not separated. A global section is determined by three numbers, but the values of that section over X and Y determine only two of those numbers. So while we can glue any two sections over X and Y, we cannot glue them uniquely. Let X be the real line, and let F be the set of bounded continuous functions on U. This is not a sheaf because it is not always possible to glue. For example, let U be the set of all X such that X less than I. The identity function F equals X is bounded on each UI. Consequently, we get a section C on UI. However, these sections do not glue, because the function F is not bounded on the real line. Consequently, F is a presheaf, but not a sheaf. In fact, F is separated because it is a sub-presheaf of the sheaf of continuous functions, turning a presheaf into a sheaf. It is frequently useful to take the data contained in a presheaf and to express it as a sheaf. It turns out that there is a best possible way to do this. It takes a presheaf F and produces a new sheaf AF called the sheaving, sheafification or sheaf associated to the presheaf F. A is called the sheaving functor, sheafification functor, or associated sheaf functor. There is a natural morphism of presheaves I, FAF that has the universal property that for any sheaf G and any morphism of presheaves F, FG, there is a unique morphism of sheaves such that in fact, A is the left adjoint functor to the inclusion functor, from the category of sheaves to the category of presheaves, and I is the unit of the adjunction. In this way, the category of sheaves turns into a Giraud subcategory of presheaves. One concrete way of constructing the sheaf AF is to identify it with the sheaf of sections of an appropriate topological space. This space is analogous to the et or A space of a sheaf. Briefly, the underlying set of the topological space is the disjoint union of the stalks of F, denoted SPE acute F. There is a natural map phi SPE acute Fx that sends each germ to the point of X over which it lies. For each open set U and each section S of F over U, we define a section of phi that sends X to the germ Sx. Then SPE acute F is given the finest topology for which all sections are continuous, and AF is the sheaf of continuous sections of phi for this topology. There are other constructions of the sheaf AF. In particular, Groth and Converdia define a functor L from presheaves to presheaves which, when applied to a presheaf, yields a separated presheaf, and when applied to a separated presheaf, yields a sheaf. Applying the functor L twice therefore turns a presheaf into a sheaf, and in fact LLF is the associated sheaf AF. Operations. If K is a subsheaf of a sheaf F of abelian groups, then the quotient sheaf Q is the sheaf associated to the presheaf. In other words, the quotient sheaf fits into an exact sequence of sheaves of abelian groups. Let Fg be sheaves of abelian groups. The set of morphisms of sheaves from F to G forms an abelian group. The sheaf Hom of F and G, denoted by, is the sheaf of abelian groups, whereas the sheaf on U given by the tensor product of F and G is the sheaf associated to the presheaf. All of these operations extend to sheaves of modules over a sheaf of rings A. The above is the special case when A is the constant sheaf.